Hello Calculus, and welcome back to part 2 of the video notes for optimization. For this problem, we're going to be using some Pythagorean theorem, and we're going to be talking about distance, rate, time, which is another classic quantity we're interested in analyzing in calculus. So for the example, an island, we'll call this the island, is 2 miles due north of the closest point along a straight shoreline. So that means 2 miles right here. A visitor is staying at a cabin on the shore that is 6 miles west of that point. The visitor is planning to go from the cabin to the island. Suppose that the visitor runs at a rate of 8 miles per hour and swims at a rate of 3 miles per hour. How far should the visitor run before swimming to minimize the time it takes to reach the island? So it looks like we're going to have someone who takes off along the beach and then at some unknown point is going to swim on a diagonal directly to the island, which is the goal. So we're going to be looking at distance, rate, time, and we're going to look at two different expressions. Ultimately, we're trying to minimize the time. So we need to create an equation that represents the total time for travel. So if you look at your distance, rate, time problem, you can solve for the variable time by dividing both sides by r. So I know that my total time is the distance spent running divided by the speed that I run plus the distance I spend swimming divided by the speed that I swim. Now some of these aren't actually variables. Distance spent running, the speed that I run is 8. Distance spent swimming, and the speed that I swim is 3. So one of the things in the strategy is to take an equation, this is an equation, and make sure it's in terms of a single variable. So that's where our sub-equations or our supporting equations come into play. Let's take a look at this picture here. Let's say that x is the distance that the visitor runs, because ultimately the question is how far should they run? So that's our goal, x. That means we're going to put an x in the first numerator of our equation. Now we'd like to use the rest of the information in the problem to figure out how to write this blue distance here for the swim in terms of x. So let's start with the shoreline. I know that I have 6 miles total, and I know that I'm going to run x of those. The leftover amount is 6 minus x. Well, now we can use the 6 minus x and the 2 to solve for our hypotenuse with the Pythagorean theorem. 6 minus x, quantity squared, plus 2, quantity squared, equals c squared, which means that our numerator, and if we fully simplify this, we should get x squared minus 12x plus 40. Go ahead and pause the video and work out that algebra to make sure that you get the same result. So this is the numerator of the second term in our equation. So we're going to put x squared minus 12x plus 40. Now let's talk about some domain restrictions. X is the distance that is run on the beach, which means x should be something between 0 and then the farthest distance he could run on the beach is 6. So the most he could run on the beach is 6, and the least he could run on the beach is 0. And then he would be swimming from either of those points. Now we're trying to minimize, so we've got 2 potential endpoints plus the derivative of this function, which is going to lead us to a critical value that could also be the minimum. So let's take the derivative of this equation right here. T prime is equal to 1/8, which is the derivative of x over 8, plus 1/3, and then we know that for the derivative of a radical, we're going to do 1 over 2 times that radical. But this is also chain rule because there's a function inside the radical, which is going to give us times 2x minus 12. So I like to simplify my expressions as much as possible, and I can't help but notice that I've got a spare 2 in all of these terms. We're going to set this equal to 0 and solve. So 0 equals 1/8 plus 1/3, except I'm not going to use the 1 anymore because I have a value to put in the numerator, which is x minus 6, times the square root of all of that. Multiply everything by the common denominator, which in this case I'm going to say is 24 rad x. And so that's going to give me the equation 0 equals 3 square root of x squared minus 12x plus 40. And then over here, the 3 and the radical will cancel, so this is just basically times 8. And I have got to solve this wonderful equation for x. And so this is a radical expression. I'm going to rearrange the terms so that the radical is isolated. This is going to give me the square root of x squared minus 12x plus 40 equals 48 minus 8x all over 3. And then I'm going to square both sides. That's going to eliminate the radical from my problem and leave me with x squared minus 12x plus 40 equals over 9. So we're going to multiply that 9 to the other side. And then in my numerator, I've got 48 minus 8x squared. So I've got 2,304 minus 768 plus 64x squared. Oh, just running out of room here. Multiply the 9 to the other side. I've got 9x squared minus 108x plus 360 equals all of that numerator over there. 4 minus 768 plus 64x squared. Oh, moved my, oh, okay, I'm just gonna move that. Okay, so we know what the numbers are, we can't really see them. We're gonna bring all of our terms to one side, and that's gonna leave us with 0 equals 64 minus 9, which is 55x squared. Hopefully we get a common term in here. We've got negative 678 plus 108 gives us 660x. And then we've got 2304 minus 360, which is 1944. And then we're going to plug this guy into our quadratic formula. So I, instead of doing quadratic formula, went ahead and used my graphing calculator. And I'm going to pull that up here. And I'm just going to graph it. Y equals, and it was 55x squared minus 660x plus 1944. And so to solve this, I like to take a peep at the graph and just make sure it has x-intercepts that can be solved. And so my window settings don't seem to be zoomed correctly, so I'm going to do a quick zoom standard. And then hopefully our function crosses the x-axis. There we go. So it looks like we got two potential solutions. So I can always calculate the zeros, and that is going to give me the solution to this function. So let's get our cursor so that I can see it, and it's to the left of the x-intercept that I'm trying to estimate. There, whoop, too far, that's the right. So there's the left side, and then right bound, we're gonna hit right one more time, hit enter again, and estimate. So we've got about 5.19 for our first zero, and we wanna do that again. So store that answer in your memory or write it down. We're gonna calculate 0 again. This time, the left bound, let's see if I can get this just right. So that's definitely to the right of the 0, so I'm going to go 1 to the left and hit enter, and then 1 to the right and hit enter again. and I'm going to estimate this 0, which is about 6.8. So I've got two potential zeros here, 5.19 and 6.08. Now, that's the interesting thing, and one of the reasons it's so important to set your boundaries. This 6-0 answer doesn't work because the most I can run along the beach is 6. So I'm going to limit myself to 5.19, and then 0, and then 6, I don't know why I crossed that one out, as my potential minimized times. So then what I do from here is I plug in each of these times to our t equation and see which one produces the minimum overall time. So I'm going to quit here. I'm going to clear this out, and I'm going to write my t equation in y equals. And so that's going to be x over 8 plus, and then we have that beautiful fraction, which will be much easier to type in the unsimplified version. So if you remember, before I squared it, it was 6 minus x squared plus 2 squared. And I'm going to go back to that version just to save me a little bit of time. So I've got the square root of 6 minus x squared, quantity squared, plus 2 squared. Good. Close out that parenthesis. I don't think that outer one is necessary, over 3. And then generally I'll set my table to ask, and I'll plug in my values from there. So I am going to head to the table, and I'm going to ask my 3 potential minimums. So I can run 0 miles along the beach and swim the whole way, and it'll take me about 2.1 hours. I can go 5.19, along the beach, and the less than a mile, so that's shorter. And then I can run the entire 6 miles and swim the rest. And I'm gonna get, can I decimal that? No, 17 divided by 12. So let's try it. 17 divided by 12. 1.42. So that's a little bit longer. So the shortest time it's going to be is 1.368 hours, and that's if I run 5.19 miles and then swim the remaining 0.81 miles, approximately. And so that is how far the visitor should run. So this one right here, oops, I just erased it, is our minimum. Okay. Owners of a car rental company have determined that if they charge customers P dollars per day to rent a car, where there's a restriction, the number of cars N they rent per day can be modeled by the function N in terms of P is equal to 1,000 minus 5P. If they charge 50 or less, they'll rent all of their cars. If they charge 200 per day or more, they'll not rent any cars. Assuming the owners plan on charging something in between, how much should they charge to maximize their revenue? So your revenue is the total number of cars you sell times how much you charge for that. So what we're going to do here is we're going to say, oops, I'm in still bright yellow, revenue in terms of how much they charge is equal to the number of cars they can rent per day times how much they charge to rent them. And so we're just going to maximize this function by finding the derivative. And I'm going to go ahead and use product rule. So I'm going to get negative 5 times P plus 1,000 minus 5P. I'm going to set that equal to 0, which is 1,000 minus 10P. And then P equals 1,000. That means that P equals 100. So they should charge $100 per day to rent a car. And then let's just double check that, because we know that if they charge $50 a day, they'll rent all of their cars. So what is their revenue if they do 50? Revenue for $50 a day is 1,000 minus 5 times 50. times 50. Type that into a calculator, and you get 1,000 times 50, $37,500 a day. Compare that with our critical value potential maximum. 1,000 minus 5 times 100 times 100. And you get for that value, you only get 5,000 a day. Did I only times by 10? I only times by 10. Just kidding. 50,000. I was like, wow, that doesn't look like it's worth it at all. And then again, if you charge 200, plugging in 200 to this function will get you 0, and that means you're not renting any cars, so you're not making any profit. So for sure, $100 a day maximizes our profit. This is the conclusion of part 2 of the video notes. Thank you for watching, and we'll finish the last 2 examples in part 3.